Okay, so we're on to the next video. So we're still talking about the factors. Let me just change this up to the typical red I use. We're going to be covering today factors affecting basically the rate of an SN reaction. So that's SN reaction, the nucleophilic substitution reaction. So factors affecting it. So we already covered the first factor. We did that in the last video, and that's the which halogen identity. So what this meant, right? We said that a carbon-fluorine bond was the strongest, followed by a carbon-chlorine bond, followed by a carbon-bromine bond, followed by a carbon-iodine bond. So right, we had said that iodine has the largest radius, so it is the best leaving group, and that the carbon-fluorine bond was the strongest, so it was the worst leaving group. So that was the first one, the identity of the halogen on the haloalkane. Number two, this is the one that we're going to be just covering in this quick video, and then we're going to cover the third one. The second one is basically the identity of the alkane. So what this means is that, you know, we've already covered this in a previous video, but it affects it, whether it's a primary, a secondary, or a tertiary carbon. So we're going to quickly review this like we've done in the other video, and then we'll get on to the next one. So remember that you know, the rate depends on the type of alkane there are, because we said tertiary versus secondary versus primary alkanes. Tertiary alkanes underwent the SN1 mechanism, which means that it only depends on one molecule, not substitution, nucleophilic, that relies on one. So our rate, as you remember, hopefully, is equal to K times the haloalkane identity. Secondary, these can undergo both. They can undergo SN1 or they can undergo SN2. And we're going to see in the next video that we can kind of force it to go to SN1 or SN2 depending on our choice of solvent and depending on the stability. You know, like we said with the inductive effect with tertiary, it's a stable carbocation. If we stabilize a carbocation, you go through SN1. If you destabilize the carbocation, you can go through an SN2 mechanism. And we're going to see how solvents can do that in the next video. So basically our rate can be both, right? Our rate can be either the SN1 mechanism or the SN2, which was K, the nucleophile, the concentration of the nucleophile, multiplied by the concentration of the haloalkane. Or our primaries always undergo SN2, so there's no question there, right? Tertiary SN1, primary SN2, and secondary, we can push it towards SN1 or SN2. It depends on the solvent, and these solvents will be used in both these circumstances too. So the last one, SN2 mechanism, right? It depends, it's bimolecular. It depends on two different molecules. So the molecules that it depends on, the rate is equal to K times the nucleophile multiplied by the concentration of the haloalkane. So those are the factors that affect the rate. That's why this is a factor that affects the rate of reaction, right? An SN1 mechanism is affected by only the haloalkane. An SN1, SN2 is affected either by this or by this, depending if it's undergoing SN1 or SN2 substitution. And SN2s are affected, so primary alcohols are affected by both the nucleophile and the haloalkane. So the rate can depend on multiple things. So right, if we took this rate reaction, this rate, and we had a very low concentration of the nucleophile and a high concentration of the haloalkane, it can be slow. Or we can do the converse. We can have a high concentration of the nucleophile and a low concentration of the haloalkane. So basically we can change this. We can change the concentrations. We can change the concentrations of more things. Whereas with the SN1, we could only increase the concentration up to basically its maximum solubility. So okay, join me for the next video. We're going to be talking about the choice of solvents. Thank you.